Welcome to Structure Analysis 1. Now, inelastic strain energy, let us start with theory first. When the bar is stretched only up to elastic limit, which is point A, the deformation will be disappear completely on removal of the load and there will be no residual deformation. The strain energy stored in the bar is then known as elastic strain energy. If, however, bar is loaded up to point B beyond the elastic limit A, the deformation will not disappear completely on the removal of the load. During the loading done is equal to the area under the curve, which is OA, B, C, and D, or OABD. Okay. When the load is removed, the load deflection follow the line BD and a permanent elongation OD remain OD, being known as the permanent set. Hence, the recovered strain energy is only the one represented by the triangle B, C, and D. This recoverable energy is known as elastic strain energy, while the area OABDO represent the inelastic strain energy. OABO, ABDO. This area is remain inelastic area. Strain energy of prismatic bar with varying section. Let us see the section shown in figure 4.A, so 4.1C, in which A1, A2, and A3, three of them are with different material, have different dimensions. Now, strain energy is given by U is equal to P square L upon 2AE. Total strain energy is equal to summation of P square L upon 2AE, in which P square upon 2E is common for such bar, but dimensions like length and area are differ. Now, strain energy stored in prismatic bar under its own weight. Consider a prismatic bar of length L hanging freely as shown in figure. Consider small element of bar dx at distance x from the lower end. Let E is equal to cross-sectional area of the bar, gamma is equal to unit weight of the material, axial forces Px in the direction of below. Okay, Px is equal to gamma into Ax. Strain energy equation for small element is equal to Ux is equal to P square x dx divided by 2 into Ae. Total strain energy as per the equation U is equal to 0 to L P square dx upon 2A. After solving and put the value of all material, we can get the gamma cube Al cube divided by 6E, which is our equation for strain energy stored in the prismatic bar. Now, strain Energy due to gradual loading. Consider a bar of length L, uniform section subjected to gradual load P. Okay, in figure we can see load versus deformation diagram and deformation versus resistance diagram. Both are linear. Okay, since the load is applied gradually, it increases from 0 to P. Average load is considered work done on the bar is equal to area of the load minus deformation diagram, which is equal to 1 half P into delta L. Now work stored in the bar is equal to area of the resistance minus deformation diagram is equal to 1 half minus R into delta L. In other words, it is equal to 1 half into gamma into A to delta L, which is equation 2. Now work done is equal to work stored. That's why 1 half P into delta L is equal to 1 half delta into A into delta L. Delta L cut 1 half out. We have now only P is equal to sigma into A. That is the equation of stress. Sigma is equal to load upon area or pressure upon area. Now strain energy. Strain energy is equal to 1 half into R into delta L. R is equal to, we know that, sigma into A. That's why I put it in 1 half sigma into A into delta L. But we know that delta L is equal to E into L from the equation of E. Strain is equal to change in length divided by original length. So put the value of delta L from the strain energy. We got 1 half into gamma into A into epsilon into L is equal to 1 half into gamma into A into sigma divided by E into L. Okay. From this exercise, we can get the equation U is equal to sigma square upon 2E into V. Strain energy due to sudden loading. When the load is applied suddenly, the value of the load is P throughout the deformation. In above case, we can show that the load versus deformation diagram and resistance versus deformation diagram both are same. But in this case, the load versus deformation diagram and the resistance versus deformation diagram are differ. Okay. Now resistance R increases from 0 to R. Work stored in the bar is equal to 1 half into R into delta L. Put the R value as a sigma into A. We get 1 half sigma into A into delta L. Now work done is equal to work stored is equal to sigma into 2P upon A. Okay. Hence the maximum stress inten in intensity due to a suddenly applied load is twice the stress intensity produced by the load of the same magnitude applied gradually. Strain energy due to impact load. Load P is dropped through a height. Sorry. Uh, we can continue this in our next lecture.